let's just jump straight in. Who has not heard this saying before? Nobody. Excellent. That's what I expected. Who said it? Like, who's doled it out on a pull request, maybe? Sorry? Donald Knuth did say it originally. That's very good. Who said it themselves? Who's left this comment on a pull request or replied to someone? No one? Excellent. Who's heard it being said to them? A few more hands. Now the big question, who agrees with it? Okay, we have some people. Excellent. So I think this little 8-word sentence, 8? Yes, 8 words, it kind of gets a bad rap. And I think a lot of people maybe don't agree with it or think it's a bad thing that it's kind of gotten such notoriety or popularity. I kind of do agree with what Donald Knuth is trying to say, but I think that he's sort of misrepresented. So the way that this has been said to me in the past would be, for example, if there's a pull request and someone has written, let's say there's a bunch of link statements, a bunch of link queries, they're all doing some filtering or some grouping or something, and you call to list, and then you filter some more, and you call to list again, etc. I'm the type of person who would come in and say, hey, maybe a for each loop would be more efficient, even though, yes, it would be longer or it would be multiple lines of code instead of one line of code or whatever, but, it'd be more efficient. And what I've found can happen is people will say, well, yeah, but premature optimization is the root of all evil. Let's leave it and see what happens. And I think that use of it is not good because you're kind of saying, let's let the users find the bugs, which is not very nice. It's kind of saying, I'm lazy, but I want to sound smart about being lazy. Not saying that's how you guys said it, but the thing is, I think it's misrepresenting what Donald Knuth meant. And the reason I think this is, so this little 8-word thing, it's not even a sentence, right? It's not a complete sentence, it's a fragment, as Microsoft Word would say. And if you take it in context of the surrounding words, I think it adds more meaning. And the thing that is unfortunate, I guess, is that surrounding context has basically been lost to time, right? Everyone just doles out these 8 words and doesn't think about it. But it turns out it's part of a larger quote. So the rest of the sentence and the one afterwards goes, we should forget about small efficiencies about 97% of the time, premature optimization, yet we shouldn't pass up our opportunities in that critical 3%. And to me, this kind of turns on its head what most people sort of use this saying to mean. Donald Knuth is saying that sometimes it's absolutely critical to think about performance and to prematurely optimize. And if you take some poetic license and maybe assume that the 97% and 3% figures are kind of plucked from thin air and not the result of exhaustive user studies, he's sort of saying sometimes performance and performance tuning and all that sort of thing is good. Turns out I do know how to format text in PowerPoint, and there's even more to this. To kind of get the full picture here, programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs, and these attempts at efficiency actually have a strong negative impact when debugging and maintenance are considered. It's a long sentence. So this kind of completes the picture for me, and this is where I fully get behind this entire sentiment. Donald Knuth was saying this in a time, it's in the 70s, right, where perhaps processor speed was maybe a little more constrained than we are now, and perhaps there was a culture of how do we get the most out of that speed, and so focusing on performance and worrying about non-critical things when they have a negative impact, I think that's a bad thing, I agree. But premature optimization, just ruling out performance thinking altogether, I definitely disagree with. And I think that's sort of how it's being misrepresented. Now, for bonus internet points, does anyone know what book or article this appeared in? It's all right, not I before I Googled it. I think it's kind of funny. So people dole out this saying as a way to say, I'm not going to do any work, but here I want to sound smart. People who like to sound smart probably also don't like go-to statements. And this quote appeared in Structured Programming with Go-To Statements in 1974, which I just kind of like as a bit of irony. So the thing is, what we get this really blunt saying, premature optimization is the root of all evil. No ifs, buts, or maybes, it's terrible. And that's not fair, and it's not really what he's saying. Coding is all about trade-offs, right? If we, as programmers, didn't have to consider the trade-offs between readability and debuggability and maintainability and illities, if we didn't have to think about those things, then we'd just be typists, right? The whole idea of most of our jobs, I think, is trying to work out, of the 400 ways I could solve this problem, what's the best way for this scenario? And you have to think about performance as one of the factors that helps you decide which way is appropriate. Sometimes you need to do things and you need to optimize for performance and throw out debuggability. And sometimes you need to go the other way, or sometimes you need to focus on readability. You have to balance these things. And you have to use the context of what you're doing and the data that you're processing to inform those decisions. So thinking about optimization is always good. Now, actually performing the optimization in a premature way, fine, maybe that's not good. But if you don't consider it, if you disregard it out of hand, that's not good. And I think what we all should be striving to do as developers and engineers and programmers, or whatever you want to call yourselves, is create a culture of performance in your team, in your organisation. To me, I think you want to get to a point where if you see some code in a pull request, which is written in either a way that you know is going to perform inefficiently, or vice versa, in a convoluted way that is harder to read, if you can create a culture of performance in your team, and you can trust that whoever wrote that code considered all of the factors and got to that point for some reason, then you don't need to worry about these sayings, and you don't need to worry about questioning that work. Now, ideally, if that work also accompanies with a comment saying, hey, I know this looks bad, but that helps. So how do you work out whether you're in this critical 3%, whether you need to focus on performance? The number one thing, so there's two things I think are equally important. So number one would be knowing the context of your execution, right? If you're writing a web application, if you have code that runs on every request, then that's going to have different needs than if you have code that runs in the admin console when someone clicks a button, which they only do once a month. If you're running a background service which does something at idle time, that's very different. If you're running a Windows app, responding to user actions in a desktop application, you can usually take a bit more time. So you've got to know where your code is running. And you have to know the shape of the data your code is processing. So where I used to work, we regularly imported data from university mainframe systems. And some of the customers would give us a single file that had every single student that had ever been to that university, and we had to process it and pluck out the data we wanted. And some of the universities were smarter and would give us the data that has changed since the previous day. So the same bit of code, we're not going to write the same bit of code to process the 10 records that have changed versus the 100,000 records for all time, right? If we don't know the shape of that data, we'll make the wrong decision. If someone says, oh yeah, we'll only give you 10 records, and they end up giving us 100,000, our stuff's not going to work right. You need to validate your assumptions about those two things as well. So again, if you, let's say in that example, if we're given the changes that have happened, you need to know roughly how many that's going to be, and you need to then talk to your clients, potentially. You need to validate that that assumption is correct. And you need to know the worst case for that as well. What if there's a bulk update and every record gets updated? What do you do then? If your code, even the context of your execution, there's worst cases there as well. So some of these imports would run at 1 a.m. Overnight, we'd process this file, everything's fine. No one's using the system at 1 a.m. But as systems, the files grew and things take longer, what happens if your 1 a.m. import starts taking 10 hours to run? Now you're running into people using the system, so what does that do? Or what if your daily import takes 26 hours to run? Do you run it twice? Do you run it once straight after each other and then they get offset, or do you skip a day? You've got to consider the worst case. You've got to factor all these things in. And you need to always be thinking about the bigger picture. So with performance tuning, it can be really tempting to take a method that does some little bit of work and really sort of drill down on it and focus in and how can I make this as fast as possible. But if you do that, if you've got some code that imports 10 records and you focus on the method that imports 1 record, no matter how fast you make that, if it now processes 100,000 records, it's still going to be slow. So you need to step back and think about, what data structures am I using? Am I reading everything into a list and processing that list? Well, maybe instead of getting the processing fast, I want to use something other than a list, right? Don't read it all into memory or use a stream or something like that. But then, if you can, get to the point where you know what your hot path is, you know the answers to all these questions, micro-benchmarking and focusing in on that one thing is by far the easiest way to reason about performance. Because essentially, that was loud. Essentially, there's one way to actually do performance tuning. You have to measure your code. You have to measure what your code was doing, change it, measure it again. Maybe you want to make 5 different versions of it and measure them all. Just measure. It's the only way to know. You can't look at a piece of code and know whether it's going to perform well or not. Because you don't know all those other things. You don't know when it runs. Which brings us to this code, which is code that I saw in a pull request that sparked this whole talk because I did the opposite of everything I've been saying, and I left a comment that said, don't do that, that's slow and uses too much memory. Well, the first thing I did actually was look at this line of code and go, hang on, what are we doing here? What does the aggregate method do again? Because I didn't really use it, hadn't really used it much. Data in this case is a list of strings. And for anyone who hasn't used the aggregate method, it's one of the link extension methods. This takes all the strings in this list and puts them into one string which is comma separated. So it does a string.join, essentially. So the code has a couple of problems, I think. It has a readability problem because string.join would have been clearer in what its intentions are. And I know from my experience that link performs, generally speaking, worse than the non-link version of whatever it is. But without quantifying that, it's kind of not helpful, right? How slow is too slow? When does this code run? Does it run constantly or does it run once? And then uses too much memory. Well, I can make this use less memory, but how much is too much, right? Is this running on a Raspberry Pi or is it running on a Xeon? Well, I guess that's not a measure of memory, but So anyway, I left this comment and it was the wrong thing to do, so I deleted my comment and I said, oh, you know what? Let's benchmark it. So how do we benchmark some code? This is kind of the simplest, probably, first type of benchmarking code people write. And it has a few problems. Does anyone want to have a shout out?
Well, you're not granular enough on the timing. You're looking at milliseconds, and you probably need to be more than that.
Potentially, not granular enough, that's cool. Datetime has a ticks property, so you can get more precision. Any other? There's a couple of, yeah?
Maybe 100 is not enough.
Maybe 100 is not enough, that's a good point.
You're going to load on the machine.
Sorry?
You're going to load on the machine.
Load on the machine, it's true. So there's a better version. And the easy way to point out the problems with this one is to show you the better version. So there's a few things we're doing here. And I'll just talk through roughly. So the first thing is setting the priority of the process and the thread to high. And the idea here is you want to measure, if I'm trying to improve some code, then I've probably got an idea of what's wrong with it, but I want to measure the current code, and I want to measure my new idea, and I want to compare the two. So in order to be able to compare two runs, I need them to sort of be as clean as possible, right? If I measure my old code, and then I get, I don't know, 3 seconds, great. Now I measure my new code, but in the middle of that run, my virus scanner kicks in, or Chrome decides to use another 300 meg of RAM or something. That's going to affect my results, right? So try to get the benchmark to be the most important thing to run. The next thing that happens is we call the function once, and that's to get the JIT overhead. So .NET compiles to IL. IL is then run through the JIT compiler, the just-in-time compiler, and it optimizes your code, and it converts it to assembly and runs it and all the rest of that stuff. But all those things have an overhead. So if you have that overhead of work done within your measurements, then you're measuring more than just your code. So the idea is do it first, get it out of the way. Next up, we use a stopwatch instead of date time. And this is probably the most important part. Date time and stopwatch both measure to the tick level, but so they're both as precise, but they're not as granular, which is to your point before. So if you were to have a tight loop and just output datetime.ticks and stopwatch.ticks, the value of the datetime.ticks would just not change as often. It's not as granular. It's just as precise, but its sampling is less. So always use a stopwatch. Then we kick off garbage collection, and again, that's just to try to make the two runs comparable. You don't want garbage collection to... garbage collection is going to affect your timing, and that's fine if it's within one run of one piece of code. But if garbage from the old code is having to be cleaned up while you're running the new code, that's going to not help. And then we run our code and then we think. Now, 100 not being enough, that's a very good point, and that's something you need to know about the context of what your code is doing. And that's also going to matter roughly how long your code takes. If you're measuring a function that takes 3 to 4 seconds, then maybe 100 is enough and maybe milliseconds is correct. But if you're looking at really micro benchmarks and you're talking about functions that take nanoseconds, you might want to run it more often. The thing is, all of this code here is rubbish. Don't use it. There's a much better way, and that is to use benchmark.net. So all of these problems that we're trying to solve with this little iterative bits of improvement are basically solved for us by benchmark.net, and it's a really awesome library. So it's supported by the .NET Foundation, which just means it's not going anywhere anytime soon. It's used internally by Microsoft heaps, and in fact, one of the developers on it works for Microsoft now. And it's super powerful. So it can benchmark .NET, the full framework, .NET Core. You can use Mono. You can compare different JIT algorithms. You can compare different bitness. It can measure a whole bunch of different stuff. And it's got plugins and extensions and all sorts of things. It's by far the easiest way to do it. And so the way it works is really dry and boring, and I'm not going to talk about it. So I'm just going to demo it. But it is slow. And the reason it's slow is because it's really thorough. And you'll see why in a minute, but I just say this to warn you, this is the only demo. The rest is pre-prepared numbers. So let's write a benchmark. I have here a console application, and all I've done is added a reference to benchmark.net from NuGet and done a build so that it downloads once, just so that we don't have Wi-Fi problems. No other cheating involved. So the way you run a benchmark, the way you write a benchmark.net benchmark is you write this simple console app, and we just tell benchmark.net, we tell our runner to run our benchmarks. The easiest way to do it is to just use the run method, and you just give it the class that contains your benchmarks. So I'm using this class. It doesn't have to be this one. It can be another one. There's also a thing called a benchmark switcher, which kind of gives you a nice command line interface for selecting which benchmark you want to run. And as you build up a library of these things, that one's a good one to use. And then the way you tell it which methods are benchmarks in your program is simply with the benchmark attribute. So it kind of feels a lot like writing a unit test, right? We have a function, we tag it with an attribute, that's it. Really easy, knows how to do it. And so we'll just write our little benchmark. So we'll write the old code version first. If I can remember what it is. You know what? I should probably define some data first, and then I won't have to fight Rosalind so much. So we're just going to have a simple array of data just for this example. And I'm going to be really lazy. I'm going to say 10 and... So we have an array of 10 strings. Pretty boring. And we write some code. And there's our method. Now, one little quirk to notice here is that I'm returning a value. Best practice with benchmarks is always return a value from your benchmark, just so that nothing in the compiler or the jitter or the runtime or anything else decides that your code can be improved and sped up in some way. Like, for example, if the runtime knows that a method doesn't have any side effects and decides to just not call it, well, that's going to really throw off your benchmark, and your numbers are going to be really good, but in your real-world code, it's probably not going to be applicable. So that's kind of rule to remember number one. And so then we'll just write the good version. So this is what I personally would have done for this code. And so you can sort of see, well, I think string.join is more readable. It's certainly more readable if you're familiar with the string.join method more than you are with the aggregate method. But we can't observe performance, right? So this is why we run benchmarks. And this is it. This is the total thing. I can run this now. I'm actually going to do one more thing, though. I'm going to put in here a parameter called baseline. I'm going to set to true. And I'm just going to do that because that's our code we're comparing against, right? We want to improve this code, so we're going to compare against this. And now I can run it. That's all I have to do. The thing to check number 2 is up here, and that is that it's a release build. Always benchmark release builds. In fact, benchmark.net will simply refuse to run if you do a debug build. So we run our console app, which is building. Woo. And so this is going to run. And I'll talk about what it's doing in a minute, but you can sort of start to see some numbers already. So we have 1 million runs, 1 million operations, and we're hovering around 630-ish nanoseconds per operation. So what it's doing is it's running this code, so certainly more than 100 times, right, 1 million times, but it's then doing those runs. So each one of these is called an iteration. It's running these iterations, and it's running as many as it, until it's happy, essentially. So it's looking at the numbers, it's looking at how the spread of results is and trying to just smooth out any spikes, it sort of waits to let things settle down so there's a consistent results. And so now we're doing another run. So that first run was for presumably the aggregate method. And what benchmark.net does is it generates a brand new exe that it runs for each benchmark you write. So all that garbage collection and thread priority and all that stuff that we were doing before, it just makes it all easier by having an exe that just does this one job. So there's no sort of way the garbage collection from one run can contaminate the next run, because at the end of one run, that whole process just goes away, right? But that's what makes it thorough, and that's what kind of makes it slow. So that took a minute for 2 very simple methods, and for doing no memory analysis either. So it can take a while the more you do. So what happens at the end of the run is you get this table of results. And you can see here aggregate took 616 nanoseconds on average, and string.join took 245. It's pretty clearly string.join's better. Our scaled column here tells us that in spades. And in fact, so scaled comes from that baseline parameter. So I said aggregate was the baseline, which means it's always going to be 1. If you're comparing a bunch of different approaches, that's a really easy way, because all you do is look at the scale column, and whichever number is smaller, just go with that one. And if there's a number that's bigger, you've made it worse. But yeah, so what benchmark does, I'll just scroll up a bit here. So you can see here, well, hopefully you can see, it says it's executing this crazy named exe. So it's generated this program just to run my string.join benchmark. And then it runs it in a few different stages. So firstly, we have the pilot stage here. And you can see the number of operations here is increasing. So it tries to determine what's a good number of times to run this code so that it doesn't take forever, but we get a decent set of results from it. And so it's settled on 2 million for this one. And you can already start to see it was 1 million for the slower code, and now it's 2 million. Well, you can already start to see this one's clearly, obviously better, right? Then, excuse me, there are 20 runs to measure the overhead. So when you're measuring your code you wrote to measure your code takes time, right? So benchmark.net is running 2 million operations of our code 20 times to measure its own time so that it can subtract that from the later figures. Then it warms up our code, so it's done 9 runs to warm up, so that's to get rid of JIT overhead, that sort of thing. And that's gonna become much more critical so the new tiered compilation, which you might have heard of in .NET. So it used to be that the JIT would optimize your code when you first ran it. Now with tiered compilation, there's stages of optimization it does, depending on how often you run your code, like for each method. And the more your method is run, the longer the JIT will spend optimizing your code. So getting that warm-up done is going to be more important. And then it does the actual run. And so 34 iterations at 2 million each, right? That's fairly exhaustively exercising our code. And then calculate the results. So it's really thorough. You get super detailed numbers if you want them, or you just look at the scale column and go with the lowest one. It's easy. Oh, that's better. So what do the results look like? So in the real world, when I ran across this code, I actually tried 5 different benchmarks. And so the real benchmark I ran looked like, well, this in the next slide. And there's a couple more features to talk about here. So firstly, up the top, we have memory diagnoser and rplot exporter. So this is starting to bring in some of the extra things you can add on to benchmarks. So memory diagnoser will tell us how much memory is used by each benchmark. It'll tell us about garbage collection, how long was spent, how many garbage collections there were and how long was spent doing them. Rplot exporter just makes the pretty graphs you'll see in a minute. We have our data, that's the same. And then we have this iterations property with a params attribute. So this is like if you've ever used XUnit theories, you can specify a bunch of parameters for this property, and benchmark.net will run each benchmark in your code for each value of this property. So our 2 runs that we just demoed that took a minute, I've got 5 benchmarks in this times by 12 different values of iterations. Like this thing took, I think, around about half an hour, which is why I'm not doing it on stage. So be aware that it is thorough and it can take a while, so you want to know that. And then we have global setup. So this is kind of like class initialize, if we think to the unit test analogy. And so this is just setting up our data, but making sure that the setup of the data isn't included in the time to actually run the code. And then there's 5 things to benchmark. And this is just mainly for my own personal curiosity. So I set the baseline to string concatenation, which is using the plus equals operator on a string in a loop, right? Something that we're told never to do. This is terrible practice, right? So I figured, well, let's find out how bad it is. And then we have a string builder, which is then the good way, right? Don't do concatenation, use a string builder. Well, let's see how good it is. And then for a bit of fun, to see if it helps, I have a string builder, but I'm telling the string builder how big it needs to be before we start. Maybe that'll help. And then string.join and data.aggregate. So let's check out the results. So for between 1 and 10 strings, this is what it looks like. It's really quite hard to read, so I drew some lines. For 1 string, string concatenation wins, which kind of makes sense because it's 1 string, so you're not actually concatenating anything, right? For 2, 3, and 4 strings, 4, yeah. String builder wins for 2 and 3 strings, and then at 4 strings, the pre-initialized string builder beats it by like the tiniest little smidge. Because at some point, once it gets to a certain length, string builder allocates another one of itself to hold the rest of the string. Our string builder we've initialized has already done that work. So there's a slight overhead we're saving there. And so you kind of would look at this and you'd maybe say, well, string builder pre-initialized always wins, pretty much. So let's just always use that, right? But the thing is, this is where you've got to know how many, the context of your execution. As we get to 100 strings, there's essentially 3 good methods and 2 bad methods. And the good methods are twice as good as the bad methods. As we get to 1,000, our good methods are now 4 times as good, right? So it's exponentially different. That's 10,000 strings. If you're concatenating 10,000 strings together, I would bet that it doesn't matter which of those 3 really good methods you use. If you're coming from old code that did one of the bad ways, you're getting such an improvement that you maybe don't need to go. And this is where Donald Knuth, I think, is sort of coming from with the don't have to focus so much on it. Doesn't mean throw it out and don't improve, but maybe those 3 good methods are all the same. By the same token, anywhere between 0 and 10, you could almost argue it doesn't matter which of the whole 5 you use, right? Depending on where this code is run. Now, again, if this is on every request and you get millions of hits a day, sure, you might want to optimize this. You might want to, you want to know what your hot path is. But, consider it in context, there's not a huge difference. We're talking nanoseconds there. So 1,200 nanoseconds is the worst sort of figure. So after you're benchmarking, always got to think about what's important. What are you trying to achieve here, right? It's totally fine for readability to win. So string.join was not the best performing bit of code there, but it was by far and away the simplest piece of code, and I think it communicated what it was doing pretty well. So in this example with this pull request, that's what we went with. We just changed the string.join. And then what's the goal? Are you trying to increase the time, or are you trying to decrease the RAM? Because, so 320 character strings, string builder is faster, but it uses slightly more memory. Now again, 236 bytes of memory is not a big deal for most of us, but maybe you're running on an embedded system and it is. Maybe you're trying to reduce your RAM usage, but you don't have a CPU time problem. If you're concatenating 2 meg strings, that now flips, and string builder is less memory. So you really need to know what you're trying to achieve and what you're working with in order to evaluate what's right. Maybe allocating 3 2 meg strings and concatenating them together is a bit silly. You might want to use a stream. All right, some more fun examples. Dictionary versus iDictionary. So this one's kind of a bizarre benchmark because what we have is I'm creating one dictionary and I'm storing 2 references to it. One is a dictionary and one is an iDictionary. It's the same dictionary, just 2 references. And then the benchmarks, they loop through that dictionary and return it. That's it. So this is an empty dictionary, there's nothing in it. All we're doing is looping through an empty dictionary. The difference, though, is quite remarkable. If you use a dictionary, a concrete class instead of the interface, it's twice as fast. It also allocates no memory at all. Well, no, when it says allocates, that means on the heap. So obviously it uses memory, but it's all on the stack. Whereas the iDictionary allocates 32 bytes. Does anyone know why this is different? Boxing, very good. When you use an interface, everything you do, well, it has to be boxed and has to be stored on the heap. A dictionary, and this is true of most of the collection classes, their enumerators are designed as structs so that they don't allocate any memory and they're fast. But if you use an iDictionary, that can't hold true. The compiler can't know what the enumerator actually is because you're getting it through IEnumerable. So this is one of those times when it's really important to think about your trade-offs. It's a fairly commonly held belief that it's always better to code to the interface, not the concrete, right? I personally don't agree with it. I'm happy to debate you later, but it might be something that if you're on the hot path, if this is a performance problem for you, you might want to break that coding standard you have. You might want to question those assumptions, right? Be open to that possibility. This is a code change that we have made in the code base I work on. We have changed parameters from interfaces to concrete types because we want to remove a memory overhead. This is a real-world solution. So you kind of just got to be open to anything, and you've got to consider all the factors. Loops versus link. So old people like me like to write loops. And, well, that's not true. I like to write link as well. But, you know, swings and roundabouts. So in this example, we have 10 strings in an array. It's pretty simple. And we're just trying to find element number 5. Nothing fancy. But the interesting thing is trying to determine what's the difference between a loop and using a link extension method. And then just to go a bit further while we're here, is there a difference between first or default with a predicate, or the where method with a predicate and then first or default? So the loop's going to win. I think that's kind of obvious. It's a bit more close to the metal, right? It's got no overhead, doesn't allocate any memory. It's really fast. Link is slower. This is just a fact. But obviously it has other advantages, so don't rule it out. The interesting thing for me is that using first or default directly is not only faster, but it also uses less memory. And the reason for that is simply that deferred execution you get with link, the where method has to allocate a where iterator to remember what your predicate was, and then first or default executes that code, but it has to store that somewhere, right? And then there's the overhead of an extra method call. First or default just loops through your collection. So again, link's going to be slower, sure, but you've got to think through. It definitely has other benefits, right? The benchmark code was one line and really simple. That's a positive. The most important thing if you're ever benchmarking link, though, is make sure you are benchmarking the right thing. So I, in a previous life, wrote a link provider for to do some custom work. And because of the way that was implemented, there's no difference between first or default versus where then first or default. But that was a fact of the link provider I wrote. That's not true of all link providers, right? If you're using Link to SQL or Entity Framework and you write a benchmark to see which link statement takes longer, you've got to write that benchmark so that that link statement hits Entity Framework or Link to SQL. Otherwise, you're not comparing apples and apples. So be aware of what you're running in. And last one is string case conversions. This one's really simple. There are 4 ways to convert the case of a string, and let us benchmark them all. So the results on this one are interesting. You'll notice there are 2 graphs. So the graph on the left is the .NET Framework, and the graph on the right is .NET Core. So the interesting thing here is in .NET Framework, to lower invariant is faster. It's the fastest one. And I think I remember reading some comment or a blog post somewhere that said it was specifically designed that that one was going to be the fastest one. So as a simple tip, maybe use that all the time. In .NET Core, though, to upper invariant is faster. Now, hang on, now I don't know which one to use. So the interesting thing about this graph, or these graphs, though, is have a look at the number in the top left. .NET Framework is about twice as slow as .NET Core. And so, again, make sure you're thinking about the right things here. Instead of trying to get an extra, 50 nanoseconds by going from too lower to too lower invariant, you get a full doubling of speed by going to .NET Core. So you need to know the quirks of the environment you're working in. You need to benchmark the right thing. If you're running on .NET Full Framework, benchmark on .NET Full Framework, not .NET Core. But also consider that bigger picture and consider that, can you switch? I mean, .NET switching frameworks is obviously a big deal, but maybe you can switch a component, or maybe you can, try a different library. It might be a bigger win than focusing in on trying to eke out a few milliseconds from some existing code. But this is the pinnacle. So this is what I think everyone should subscribe to. I love this. This is my favorite piece of code from the .NET Framework. This screenshot is straight from reference-source.microsoft.com. This is the hybrid dictionary class, which I'm kind of going to guess that no one's used because it's very old. It predates generics, and I'm not sure it has any purpose anymore, but here it is. The hybrid dictionary its job is, it's a dictionary that changes how it internally stores the data you give it so that it's as fast as it can be for the amount of data it's storing. And if you were to say to me, hey, go and write a dictionary and change what backing store you use so that it's fastest depending on how many items there are, my mind would go racing and I would be like, right, okay, well, we need to monitor how slow add and remove are. We need to maybe build up some heuristics about how often add and remove might be called. You know, maybe this would be a good opportunity to put in some machine learning. I hear that's all the rage. You know, we can have this really smart collection that does this amazing work. It's going to be ideal. No, none of that. 9. That's what you want. A hybrid dictionary changes from using a linked list to a dictionary or a hash set once there are 9 items in it. It's that simple. So the code's really simple. It's really easy to debug and understand, but that doesn't mean performance was thrown out. There was exhaustive performance testing to establish that 9 is the right number. 10 is completely wrong, and 8, don't even get me started. 9 is where you want to be. But that's what, I mean, you know, I just think this is the ultimate. Besides the fact that I love how funny the comment is, and it reminds me of that Dilbert cartoon with the random number generator. But, you know, if you can get to a point where it's considering performance, it's doing, you know, decent, thorough work to establish what the performance is and what we want it to be, etc., but still have understandable, easy to write code, you know, not machine learning algorithms in a dictionary, I think that's great. In summary, should you always do the things that are faster? No. Pretty much, and that's what I'd like to think Donald Knuth was maybe talking about, is that it depends, right? Programming, it always depends. There's every question in programming can be answered by saying it depends. If you're ever in a meeting, just, yeah. But, yeah, exactly. You kind of need to be aware of that, right? So don't, you know, throw out all performance by saying premature optimization is the root of all evil, but sometimes that's the right approach. But by the same token, sometimes digging in and violating your coding standards in order to eke out another more, you know, 3 more bytes of RAM is important. That's all the slides I have. Thank you. Does anyone have any questions? Yes?
Yeah, so I was just wondering, obviously those are quite isolated examples you've shown,
yep.
Quite specific, and you've got the comparisons. If you had to try and do the same want to try and benchmark to say a more complicated piece of established business logic, how could you, have you got any examples of how you could put a framework like that into that process? And obviously there'd be a lot more dependencies to baggage along with it rather than just stuff like that. So
the question was about benchmarking more elaborate code with dependencies and business logic and all that sort of thing. And it's definitely a challenge, and it's something that you need to be careful with because it can come, you kind of don't necessarily want your baggage to affect your benchmark. And it's, so, I mean, if you, I had up there if you're using link with entity framework, for example. Well, if you're benchmarking something that accesses a database, probably the execution of your code is going to be the smallest component of whatever time that takes, right? The database hit and the network traversal and all those things is going to be huge. So you actually don't want to really benchmark that. You want to, if you can, boil it down to some essence that you can benchmark. But that's also where you need to think about algorithms more than code. So if you're processing data from a database, you're going to get improvements in your code by thinking about how you process the data and not worrying about the time it takes to get that data. Obviously, benchmarking the time it takes to get data is important as well, and you know, query tuning and all those things are super important. But you do kind of need to separate all these concepts if you can, because otherwise, yeah, you just sort of bring along too much baggage with your benchmark, and your numbers, you'll still get numbers out of it, and you'll still be able to pick a winner and all those things. It just might not have as much effect in the real world as it does in your sort of isolated environment. So you kind of need to, like, you're benchmarking in isolation, so you kind of need to get your code in that sort of same isolation, if that makes sense. Yeah.
Could you use this?
Sorry. down the front first.
So could you use this to test your baggage? So, I don't know, let's say you've got NDCs on Cosmos DB or blob storage or...
Yep. You definitely could. I mean, you can use it for these things. You just sort of have to be aware that the numbers you're getting are going to be very end-to-end, and they're going to be, they're going to be hard to compare. So, well, even this benchmark here, right? So I ran that in a minute on my laptop, not plugged into power. If I go home and plug it into the electricity, it's going to run faster, right? So that's not very useful. I'm not going to compare this run against one I do when I get back to the hotel. But right now on this machine, I can still compare those two methods to each other because they ran in the same environment. So you can do that and you can factor in your DB hits and whatever. I just wouldn't sort of put any stake in what the numbers are because it's really isolated to that time. You know, half an hour from now, you could have something else going on the network. You could be routed through a different DNS server. Anything's possible. So you just want to kind of not put too much weight in it. So there was one other question. And then,
would you use this kind of micro-benchmarking in order to spot eventual performance degradation due to code changes?
Yeah, so the question was about preventing degradation in future. And it's something that comes up a lot because how much benchmarks look like tests, that everyone wants to run them in their CI and have it fail when it takes too long. And it's definitely something you can do. There's not any built-in tools in benchmark.net to do this, but I mean, it does export all of its data to exhaustive CSV files, and you can build that infrastructure yourself. I think it's a really good idea. It's definitely something that we do have on my team, and we have performance degradation tests, but it's all about, you've got to think about the numbers a lot. You don't want to have it, this run took longer than the last run, therefore I'll fail the build. You want to have some kind of threshold. And you probably want to look more at trends than actual results. It doesn't matter if one run takes longer, but if the trend is upwards, then that's something to look at. But yeah.
I don't know if your team is CoreFX, but CoreFX has a bunch of performance tests.
Yeah.
I wonder if they are a good starting point for, if my company, say, wants to start doing performance tests, is that code base a good example? And what do you guys use for testing? If, like I said, it looks a lot like a testing framework, but I don't think it is. If so, what do you use as a testing framework to support performance tests?
So two questions. Yeah, so there's testing, there's performance stuff in CoreFX. There's a .NET performance team. It's sort of separate to CoreFX. It kind of sits across the top. And one of the guys on that team is one of the authors of benchmark.net. So they use benchmark.net. And he's still going through building up this library, but essentially the idea is that it's going to be a library of benchmarks in order to prevent regressions and all those sort of things. A lot of Microsoft internally was using XUnit performance before, but it's pretty much migrating to benchmark.net. So I would say, yes, it's a good thing to look at, but I don't know that it's sort of, it's a journey, not necessarily a finished thing that has been done. And it's also, by nature of being the core framework, it's quite complicated and covers lots of things that most of us don't need to worry about, like all the different cross-platform type things. Any other questions? Yes?
Yeah, I'm wondering more on the human level. How would you promote performance-conscious work more?
Yeah, that's an interesting question. I think certainly, introducing tools like this helps because I think it takes the humanness out of it, which is kind of funny considering you asked about the human nature. But you want to prevent an argument about performance, and having numbers and objective data is a really good way to prevent an argument. So I think encouraging the use of tools like this is a good step. If you get everyone to think about that's essentially, it starts with just making sure people are thinking about what they're doing. And so having people write benchmarks in the same way that a lot of places, you have to write a unit test for any new code you write. Well, maybe you have to write some benchmarks. Particularly if you want to prevent regressions, that might be a good step. Just having them start to think about the numbers makes it, I think, an easier conversation to have because it's objective data rather than, gut feel and seniority or any of the other factors that can come in. Yeah.
Is it possible to use benchmark.net to benchmark across different frameworks, different frameworks?
Yes.
Even different versions?
Yes, I think so. Yeah, so the attributes, so like, well, I don't have one. Yeah, so like the memory diagnoser and rplot exporter attributes, there's attributes to select the type of JIT you want to use. There's attributes to select bitness, and it will just run as many combinations as it has to. And yes, it's exhaustive. And because it generates an exe for each run, it can, I mean, it essentially generates code, then compiles the code, then runs the exe. So it can generate the code, and it can compile it with .NET Core, and then it can compile it with full framework, and away you go. Your code you write is just kind of like the shell, so it makes it easy because you don't need to worry about all that stuff. It does it for you. Yeah?
Should we be trying to run benchmarks in a fairly isolated environment? Like if I've got Slack on my machine doing stuff?
Yeah, that's an interesting question. I certainly know of a lot of people who kill every process on their machine that they can to run the benchmark. Again, it comes down to what you're going to do with the numbers. If you're going to run a benchmark and then run it again next week and compare the numbers, you probably want to do that. If you're going to run it now and just compare within this run, it doesn't really matter because it's the same environment. I tend to watch the benchmark and not go off and do something else just in case, but that's more about, if the first bit of code finishes and then the second bit starts running and something else happens. It's about preventing unknowns between these two things. Yeah. Yeah.
Is it also possible to use to benchmark on remote devices like tablet or
Not that I'm aware of. No, it doesn't really support that. But again, you're kind of looking for relative. You need to look at the numbers as relative numbers, not absolutes. The fact that this method took 200 nanoseconds in the benchmark doesn't mean it's going to take 200 nanoseconds in production. It's more about this method was twice as fast as this method. So it's going to be twice as fast on your phone, just the actual numbers might be different.
It's just that maybe the code only runs on phones. There is .NET code that only runs on phones.
That's true.
it's because some methods might be able to generate more garbage, so the garbage collector might have to run more often.
So
But because mobile devices are often memory methods that might often degrade performance because the garbage collector has to run more.
yes, that's an interesting point, actually. I wouldn't be surprised if there is something out there to help with that, possibly an extension. Yeah, that's a good point. But there probably is a way you can sort of do that anyway. I mean, there is lots of options to constrain, lots of options around garbage collection, and you can, I mean, these days you can even supply your own garbage collector, right? So I wouldn't be surprised if there is some option around that, or if it doesn't exist, it would eventually, particularly as .NET Core going cross-platform, obviously, it's going to need that. Any other, yeah?
Speaking of running it on multiple platforms, performance benchmarks, if one isn't necessarily in control of the environment, like running it in the cloud or something, would it be possible from your experience to have some sort of base case benchmark to just never change? Just some sort of algorithm that always runs in the same way, so it always takes one unit and compare things.
Yeah, I think that's a really good idea. It is hard to compare numbers, and yeah, if you're running it in the cloud, you're probably going to get a difference of numbers. So running one case first as a baseline, yeah, I think that's probably a really good idea. Oh, cool. Thank you very much.